So next, let's look at some problems that are similar to the ones you'll encounter in problem set 8. And these have to do with composite and inverse functions. So we're going to look at those concepts. So this first example, a pebble is tossed into a pond. The radius of the first circular ripple is measured to increase at a constant rate of 2.3 feet per second. What is the area enclosed by the leading ripple after 6 seconds have elapsed? How much time must elapse so that the area enclosed by the leading ripple is 300 square feet? Alright, so let's draw a picture. So we toss a pebble and it makes circular ripples moving away from that pebble. So we're following the first ripple as it kind of expands away from it. So the radius of the first circular ripple is measured to increase at a constant rate of 2.3 feet per second. So I can have the radius as a function of time is equal to 2.3 times time. So this is the rate. So if it's increasing linearly at 2.3 feet per second, then to figure out the distance, the radius, this is the rate times the time, so 2.3 times t. So it's the radius as a function of time. Now it's talking about the area. So what is the area enclosed by the leading ripple after 6 seconds? Now area is pi r squared. So area is a function of the radius. Alright, so I guess let's say area is a function of the radius. We know the formula for a circle, pi r squared. But we want to know the area as a function of time. Right? So we need a of r of t. Right? So we plug the radius equation into the area equation. So that area as a function of time is going to be pi times 2.3 t squared. Right? So 2.3 squared, 5.29 pi t squared. So we composed these two formulas basically in order to find the equation for the area as a function of time. So after 6 seconds, 5.29 pi times 6 squared, 5.29 pi times 6 squared, it's 598.28 feet squared. So that's how much area is enclosed in that situation. How much time must elapse so the area enclosed by the ripple is 300 feet. We're going to take this same equation here, the composite, and solve it for t. Okay, so we have 300 equals 5.29 pi t squared. So t squared is going to be 300 divided by 5.29 pi. So t is square root of 300 divided by 5.29 pi. I got 13.35 seconds. And that does not make sense because the area here was bigger. Oh, I think I didn't do the division correctly. Alright. Those parentheses. 300 divided by parentheses 5.29 pi. 4.24. That makes a lot more sense. 4.25 seconds. Alright. Doing the order of operation correctly is a good thing. Alright, so let's look at this example. And this is an example of doing a composition with a piecewise or multi-part function. So a plant is growing on a particular steady light source. If we apply a flash of light of high intensity green light at the time t equals 1 and measure the oxygen output of the plant, we obtain the plot below and the mathematical model given by this equation. Okay, so we look at the equation and the plot. So f of t, so f of t gives us like the oxygen output gives us the oxygen output for the plant. So f of t equals 1 if t is less than or equal to 1. So oxygen rate is going to just be steady 1 between time equals 0 and time equals 1. So it's going to steady rate. Then a t is 1 is when the flash of green light is applied. And in the equation, you can see in the graph, it's a parabola. So we have this parabolic graph right here between t is 1 and t is 3. And it's given by the equation 2/3 t squared minus 8/3 t plus 3. Okay, so we have this parabola. And then at t equals 3, it goes back to a steady output of 1. Okay. Now suppose instead we apply the flash of high intensity green light at time t equals 5. Verify that the mathematical model for this experiment is given by f of g of t, where g of t is t minus 4. Okay, so let's see what would happen. So if this is what happens when you apply a flash of light at t is 1, it would make sense that if you apply the flash of light at t equals 5, it's going to sort of be steady at 1 until t is 5. And then we have our parabola there for 2 seconds, from 5 to 7. The parabola will look exactly the same. And then it would go back to like a steady value of 1. Okay? So let's look at this composition and see if it makes sense with this new graph. So we want to do f of g of t, where g of t equals t minus 4. Okay? So basically, if we're doing this composition in this function, when we're doing a composition, we basically say everywhere we see t, we replace it by the equation for g of t. So our equation for g of t is t minus 4. So that means t gets replaced by t minus 4 in all parts of the equation. Okay? So in the first part, we have f of t equals 1. So there's no t to replace, so that just stays 1. This says if t is less than or equal to 1. Well, there is a t there, so this t gets replaced by if t minus 4 is less than or equal to 1. We can solve this to get this function is 1 if t is less than or equal to 5. So you get the t by itself. All right, the second part of the equation. Okay. All right. We replace t by t minus 4. So this is 2/3 t minus 4 squared minus 8/3 t minus 4 plus 3. Okay. And we got to change this t also, if 1 is less than or equal to t minus 4 less than or equal to 3. Okay. So we can expand this out. So let's say we have t 2/3 t squared minus 8t plus 16 minus 8/3 t plus 32 over 3 plus 3. 2/3 t squared minus 16 over 3t plus 32 over 3 minus 8/3 t plus 32 over 3 plus 3, which gives us 2/3 t squared minus 24 over 3, which is 8t, plus, let's see, 32 over 3 plus 32 over 3 plus 3. This gives me 73 over 3. So this is 2/3 t squared minus 8t plus 73 over 3. For the inequality part, add 4 everywhere. And we get 5 less than t less than 7. Okay. Last part of the equation, we have 1 if 3 is less than or equal to t minus 4. Okay, so this is going to 1, add 4 to both sides. If 7 is less than or equal to t. Okay, so let's see if this matches our graph. So we have, it's a 1 until we reach 5. So that's good there. Then we have a parabola until you get to 7, from 5 to 7. And then if t is bigger than 7, then we get 1. Okay, well, does this parabola match this one? Let's see what the vertex is. So the vertex is negative b over 2a, which is 8 over 4/3, which is at 6. Okay, so the vertex is at 6. That makes sense. If I plug in the vertex in there, 2/3 times 6 squared minus 8 times 6 plus 72 over 3. Let's see if it kind of matches what's on the graph. So 2/3 times 36 minus 48 plus 73 over 3. We get like 0.33. 0.33, which is, looks right on the graph. Right. Is it the same as this one? Like this would have been a 2 and 0.33 if they're kind of just translated. So yeah, if I plug in 2 in this one, so 2/3 times 2 squared minus 8/3 times 2 plus 3. Yeah, that's 0.33. Okay, so yeah, so just the whole parabola shifted to the new place. So it makes sense in terms of this composition.